We're skipping section 14.6, so the last section for the course and of chapter 14 is 14.7, which is on driven oscillations or forced oscillations and resonance. And what this is talking about is we've calculated previously in the previous sections the frequency of a spring and the frequency of a pendulum. Frequency of the spring depends on the spring constant and the mass on the end of the spring. The frequency of a pendulum just depends on the gravitational acceleration and the length of the pendulum. And so given those things, there is a natural frequency. So we have those equations for those things. So for example, for a pendulum, we had F is 1 over 2 pi times the square root of little g over L, where g is the gravitational acceleration wherever you happen to be. So on Earth, it's 9.8 meters per second squared, and L is the length of the pendulum. And it doesn't depend on the amplitude of the motion at all. And for the pendulum, it doesn't depend on the mass of the thing on the pendulum. So that means that everything has a sort of natural, if we generalize this, everything has a natural frequency, the frequency that it is most likely to vibrate at. And we can, if we shake something at the same frequency that it is naturally wants to vibrate at, then the amplitude of the vibration gets larger and larger and larger. And there are a lot of really cool videos illustrating, showing examples of this. We could have had a nice demo if we were in class showing it, but you can look at the videos online. I'll post some links as well. But do take a look here on this slide. There's a link to pendulum resonance, and I'll post a link to a video that you may have seen on YouTube about a bridge that broke apart because of the frequency of the wind coming through the canyon where the bridge was resonant, meaning it matched the natural frequency of the bridge and caused the amplitude of its oscillations to grow and grow and grow until it broke apart. So that's what resonance means. It means matching of the natural frequency of a system, the frequency that it wants to oscillate at, to some external forcing frequency called the driving frequency or the external frequency FEXT, shown here on the slide. If those two frequencies match, then the amplitude of the motion can grow. And in general, the frequencies don't have to match exactly, although that's primarily what we'll be talking about. But for example, if the driving frequency is exactly 2 times the natural frequency or exactly 1/2 the natural frequency, then you can also have resonance. It's not as strong as if it's 1 to 1, but you'll also have some resonance there. In my own research, we study things going on in Saturn's rings, and there's a natural frequency associated with orbits. So for the Earth, for example, that frequency is 1 revolution per year. That works out to a certain number of radians per second. That's a particular frequency, just like we calculate for a pendulum. And if some other orbiting object is gravitationally interacting with it at that same frequency, it causes big perturbations in the orbit of the first object. So there are all sorts of waves and cool things in Saturn's rings that are caused by moons whose orbital frequency is resonant with the orbital frequency of the ring particles. So what these figures are showing in the slides here are how the amplitude of the motion of a simple harmonic oscillator gets very large as the forcing frequency gets close to the natural frequency of the system. Now the difference between these different colored curves here has to do with how damped the system is, and we're skipping the details on damping, which are covered in section 14.6, but you can think of damping, for example, if you think of a child on a swing and you push the child and then the child doesn't do anything, gradually the swing will come to a stop due to friction between air drag and friction where the swing is attaching to the bar at the top. That's damping, right? It doesn't go forever. And there can be more or less of that damping, and just depending on that magnitude of that damping will affect how strongly a resonance amplitude grows. So the conceptual examples here talk, the first one is you've probably had some experience with maybe driving over a dirt road where there are these sort of ridges and your car can be sort of shuddering or vibrating. And you may have noticed that if you change your speed, that can reduce the amount of shuddering in the car. And that's because hitting those bumps at a certain, if you're driving at a certain speed, hitting those bumps corresponds to a certain frequency. And if that frequency matches the natural frequency of your car has natural frequency because it's just sitting on a bunch of shock absorbers, which are springs on the wheels, and those have their own natural frequency. So remember, for springs, the natural frequency is 1 over 2 pi times the square root of, oh my gosh, I'm going to forget. I think it's K. I can't write now either. K over M. I have to double check that. I'm going to pause. And I remembered correctly. It is K over M. I just freak out that maybe I had misremembered it. But in any event, these are two examples of two natural frequencies, and the forcing frequency matches those. Then you get a big growth in the amplitude of the motion. This first conceptual example refers to not a automobile, but a train car going over a bumpy track. The train car has its own natural frequency, sort of like a pendulum frequency. It can tip side to side, so it's like a physical pendulum. So it has some natural frequency, and if it's hitting the joints between the rails at a frequency that matches that, then it'll cause the amplitude of the motion of the train car back and forth to grow and grow and grow, and can even cause the cars to derail. And so you can just either speed up or slow down the train to change the forcing frequency so it no longer matches the natural frequency of the train car. And the last conceptual example before we work out our own example has to do with hearing. And hearing involves different frequencies. So the different tones that we hear correspond to different frequencies of the vibration of air, which causes the mechanisms in our ear to vibrate at different frequencies. And the model here of the ear taking the cochlea and sort of unraveling it shows that at different locations along it, it has a different natural frequency. And so the sound coming in excites vibrations at different locations in the cochlea depending on this incoming sound matches a frequency at a particular location because we've got a whole bunch of different natural frequencies in this system. And depending on which one has the biggest amplitude, then their nerves at that location send a signal to the brain that says, ah, that sounds like a middle C or a low note or a high note to me. So that resonant aspect is what enables us to distinguish high notes from low notes. Let's work out an example, a simple example to illustrate this, and it's just a child on a swing. This is problem number 47 in chapter 14. A child sits on a 2-meter long rope swing. If you want the child's amplitude of motion to grow, how long should you wait before pushing? how long in between pushes should you wait? And it's a little bit of a silly question because maybe you've pushed a person on a swing before and you didn't have to have taken Physics 1 to know when to push the child, but we'll explain that when we get to the answer here. How long do you wait in between pushes? Okay, so the question is, I'm pushing a kid on a swing. What's the interval that I push in order for the child's motion on the swing to be growing so that she has a better time? So I want to match the external frequency to the natural frequency. Well, this is a person on a swing, that's a pendulum. So F0 is 1 over 2 pi times the square root of g over L. And we know L equals 2 meters, and g is 9.8 meters per second squared. And the problem also, by the way, I didn't write it down, told us the mass of the kid, but that's a red herring. The mass is irrelevant for this problem. It would be the same answer no matter how big a person is on the swing. So let's just take a look at what that frequency works out to. It's 1 over 2 times pi times the square root of 9.8 divided by 2. And that gives us 0.35 hertz. And the period then, the natural period of that swing is 1 over f naught, and 1 over 0.35 is about 3. It's 2.86. So that's your answer, as simple as that. You would push every 2.86 seconds because that's the period of oscillation of the child. You push, 2.86 seconds later, the child has come back to you. So it's about 1.5 seconds out, 1.5 seconds back, and you push again. And obviously, if you pushed every 1 second, you'd look like an idiot because you would push the kid would be moving off like that, and then you would be doing this again, and there's no child there for you to be pushing. So that's why you didn't need to have a physics class to know this answer. If you're pushing a kid, you push when the kid is there, and that all this does is tell you how frequently that is. So it's every 2.86 seconds. And the other thing I wanted to mention is that we had said that it doesn't necessarily have to be matching this frequency. So suppose, for example, you pushed every 1.43 seconds. Well, if you're pushing every 1.43 seconds, that means you're also pushing every 2.86 seconds. Half of your pushes are in empty space when the child is at the far extent, but the other half are the child is there. So you would still grow the amplitude. What about if you pushed every 2.86 times 2 is 5.72. If you pushed every 5.72 seconds, it would also give the child a good ride on the swing because you would push 2.86 seconds later, the child is back there and saying, hey, push me again, but maybe you're checking messages on your phone and you forget, but you wait another 2.86 seconds and the child comes back, and then you give a push and you're matching so that resonant frequency, you're not matching it 1-to-1, but you're matching it 2-to-1, and that would still grow the amplitude, but not as much as if you matched it perfectly. So that's how resonances work and forced oscillations work. You're just matching the frequency, or if you want to think about it, matching the period of the natural frequency with some external forcing frequency.